So, hello everyone, welcome to this problem solving session. The content for this week was mainly on PN junction. So, all type of PN junction was discussed. So, basically, let me summarize what was covered in this week's sessions. Basically, first module was the introduction to PN junction. The PN junction is basically when you like make like a part of the semiconductor as P and other part as N, and when there is like the P type material is buried into the N type material, then there is a junction form, and there like a lot of different kind of electrostatics and charge transfer take place. So that talks about the PN junction and why it behaves like the normal like PN junction diodes or photodiodes uh, is the fundamental to this all those sort of devices. The PN junction is mainly the main device is your rectifier or uh, like diodes. So basically, they are used in like normal everyday circuits in rectification. So so these are mainly covered with the diode. Then other application is the photodetectors. The photodetectors also one of the classic example of your PN junction, and other some advanced junctions. Even BJT or MOSFET is basically is also contains the PN junction is also used form in the BJT and MOSFET also. The reason to study this is PN junction is basically to have like this. This is the fundamental building block of all the electron devices. Per se, BJT, high electron mobility transistors, and all the other devices which use some kind of transistors or diode diode which or solid state devices per se use this PN junction and this. So that's why it's important. So there are different kind of PN junction exist. Like the one is like normal PN junction with similar material for P and N type. Then you can make a different material that is a heterojunction you call, and then that is primarily used in HBT or heterojunction bipolar transistors, and primarily used in low noise amplifiers and those kind of applications. And then second class of the junction is PIN junction. So basically, you sandwich a intrinsic region in between the P and N region. So what is the PN junction? Like if you join the so analogically uh, by like if you join this P and N type semiconductor together, then they will form a junction. And actually, in the practical devices, this is oversimplification that any two metal pieces or semiconductor pieces you will join and then will they form the junction. That is not like the experimentally or like practical scenario. Practical scenario, there are in practical devices lot of devices uh, lot of devices uh, a lot of process involved in just to make the simple PN junction, not just like fusing two metals. Initially, that was the process when like the Shockley and Bardeen demonstrated the like a normal junction rectification and those kind of things. But now technology has moved like a greatly forward. So now this is so now let me just give a quick overview like how this. So you take a silicon wafer, and then what you do, you make a window, and like let's say you have p-type substrate, so then you will make a n-type in this so now you make a window and you quote a resistor here, and then in this other region you diffuse, you inject basically this p-type substrate has acceptor type doping in the substrate. So if you inject n-type dopant like phosphorus or arsenic, then they will form like this region. So this region is an N region, and you make a contact here with aluminum or whatever metallization you do, and this will form a PN junction. So the actual PN junction is like it's not like this kind of, but actual PN junction is made like this. So but to explain and to keep the thing in simple, like especially for this kind of basic courses, we consider this case, and we consider in this direction actually. So if you take cross section of this device at this direction, then you will see like this kind of region also. Or you let me just draw it clear. Yeah. So if you take a cross section in this cross section, then you will find this is the similar kind of region. If you neglect those other 2D effect, then like that is the simplified pictures you will get. So yeah, so now if you make a junction, so what we will ideal way. So what I will do is I will just parallelly draw the band diagram. So a band diagram basically like you draw with respect to the vacuum energy level. Yeah. So band diagram you draw with respect to the vacuum energy level. So when this P and N region are separate, so there this is your vacuum energy level is there. This is vacuum energy level, and when with respect to so each so there is one there is one concept like electron affinity. So this is the this is EC and this is EV, and the electron affinity chi is defined as chi is defined as the energy required. So the vacuum level is basically like if you want to eject out an electron from this so this vacuum energy level is like if you want to eject out an electron from a piece of semiconductor or whatever material. So the vacuum level is defined that the energy required which eject out to eject out electron, and just ejected electron will have zero kinetic energy. So basically like the that is defined as the vacuum energy level, and like this the energy required is the electron affinity, and this is the property of materials. So this for a different material it may be different, and for a particular material it will be same. So now when you when you join the when your let's say a different two pieces of semiconductors are separate, so they will have the equal they will have the equal electron affinity. So with respect to the vacuum, they will lie. They will have same vacuum energy of energy level, but the we doped one is p type, one is p type, and other is n type. So p type one will have the energy Fermi energy level closer to the valence band, and n type level will have the Fermi energy level closer to the valence band. And the intrinsic intrinsic energy level, that will be lie typically at the mid band, and here also EI will lie at the band. So now what will happen? So basically now you can see. So there is a difference when you don't join the uh, uh, sorry, yeah. So when you join this, so we last class we have seen in an equilibrium the EF is constant. So basically del EF by dx is 0. So so to make the equilibrium band diagram, so these are like when you when you brought two semiconductor pieces are separate. When you join them, then what will happen, because the Fermi energy level or chemical potentials are different, so there is a movement of charges. So now what will happen is there the Fermi level. So now when you join this these two piece of semiconductor, so one side has that electrons access, other side that holes access. So what will happen? So because here is the like the n side has the excess of holes and p side has the excess of electrons. So what will happen, like when you join this thing, this electrons will start to diffuse actually. So this will go to this side, and the whole, because this concentration, electron concentration is way lower. Like in this region, electron concentration is Ni squared divided by Na, and this side electron concentration is Nd. So if you dope with let's say 10 power 17, so this concentration, concentration of electron in p side is much smaller compared to the concentration of electron in n side. Similarly, concentration of p in p side is much higher compared to the concentration of p in n side. So p in n side is basically Ni square by Nd. So that is much lower compared to the whole concentration in p side. So because there is a concentration difference, then that movement of holes and electrons will take place. It is similar to the movement like you can it's the statistical mechanics concept. Like if you take, like for example, some particles, or like if you try to diffuse some ink in a glass of water, and you can see that visibly how the particle moving, and after some time, like because of that diffusion, like suppose you take dye in a glass, and if you inject a drop of dye in glass of water, then basically that will after some time that diffusion will take place, and like after some time your whole glass of water will take the color of this. So after some time, that after that diffusion, those equilibrium will be achieved, and similarly here is the same concept and same same thing is applied there. So what will happen? So now what is happen? So now let me draw it here. Now if so now this uh, so now so this the electron electrons will move to this side and hole will move to this side. So now because electron will move and this electron is donated by some donor. So the that donor has a positive charge. So after some movement there will be some positive charge here. So because this electrons has some ion cores remaining, so there will be some positive charge which is immobile. So because of that donor atom which you have injected into that, and like normally at room temperature or device operating temperature, these whatever doping you have done, that can't move, that can't diffuse, because to have those ion movements or charge like fixed ion movement, you need higher temperature. Especially that's why while processing, like doing this diffusion process takes around 1500 or 800 some higher temperature. So on that, this ion diffusion is significant, but at room temperature or device temperature, normally typically 300 Kelvin or so, this electron movement is feasible, but the holes the fixed ion or fixed charges movement is very less. Similarly, the hole in negative side will diffuse to this side and they will leave negative charge. So because now this positive and negative charge are separated by a distance, and then they will constitute a electric field. So as you know, the electric field is goes from positive to negative side, and this electric field since this is the opposite to the movement, so the initial diffusion it will oppose. So after some time in the such a high electric field develop, so that the your this movement of electrons and holes are seized, and that's where you say like the equilibrium has reached. So that is the case. So in an equilibrium, basically your the Fermi level or chemical potential aligns, and then you can draw the band diagram based on that. So to draw the band diagram, so this was the band diagram without contact. When you make a contact uh, in the equilibrium, so you draw the Fermi energy level as a fixed level, and let's say this is the junction, and so what will happen is like the away from the junction, this is the neutral or quasi neutral region, neutral or quasi neutral. This is also neutral region. So the in the neutral region, the properties of semiconductor will be similar to whatever in the before making junction. So this will be like in the neutral region, the this will be the conduction band, and similarly in the neutral region in p side, this will be the valence band. Will valence band will remain near to the uh, near to the near to the Fermi level will be near to the valence band. So now we can draw this uh, now we can draw now, since this until unless you change the material, this EC minus EF or band gap will remain constant. Then you can draw this and similarly here you also you can draw this yeah, so here also you can draw this. So this is EV in N side, this is EC in N side, this is EC in P side, this is EC in P side. Now Now, because of the diffusion of these carriers, there is this will be, here will be the potential drop, and you can make the junction like this. And similarly, now if you draw the now, because for a material the electron affinity is constant, then you need to do the vacuum level banding of the band actually. So now this vacuum level will look like this, and this is known as the will be vi, and this is known as the built-in potential in the semiconductors. And similarly, other level also you can draw, like the intrinsic energy level, which you can draw like this. That also will be fixed with respect to the conduction and valence band edge. Only the Fermi level will remain constant. So this is the band diagram of the p-n junction in equilibrium, of course. And so this so depending on the type of like, so depending on the type of junction, type of material or type of doping, this the charge in the depletion region will vary. So in case of uniform doping, this the charge in the p and n side. So basically it will be, so in the p side row, the charge will be q n d by epsilon, q n d by epsilon, and the charge in the negative side will be q minus q and a by epsilon. So basically, because in the p side the charge is negative and the n side charge is positive, so this is negative charge and this is negative charge. So this is negative charge, and this side this is positive. So the charge now based on the charge you can calculate the electric field. So you, if you apply the Gauss law, so from the electromagnetic field theory, so this is E dot ds, E dot ds is equals to rho v by epsilon, and you can write rho b. So E dot ds you can take, if you are taking one direction, then you can take area in cross section. So this is and this is if you can take area, and then you take this, and then you can like if you take and this rho b, you can write the cross section multiply by dx, and then like basically and this area also you can write as like width time dx. So basically this area cross section you can write as uh, width of the device time dx, and this is your cross section area times e, and integrate, this is you can write by width time dx time like the density, or you can like you can calculate the volume charge density to the surface charge density, and if you normalize by this width, then you have the surface charge density time dx by epsilon. And if you take the derivative, this is integral of sorts. Then if you take the no, this is not, yeah, if you take the derivative, then basically you will get uh, you will get dE by dx equals to rho s, that is q n d by epsilon. So this is the basic Gauss law, and based on this, like now you, since you know the charge profile in the x and y direction, you can get the electric field profile. So so for this kind of abrupt junction, you can get if you integrate this equation, you will get the field profile like this. And yeah, so this is the field profile, and similarly you can get the uh, 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 other potential functions. So this was the basic summary of the session which was there in the class, and let's just move to the problem solving session. So if you have any doubt, I will pause for some time, and let's just move to next problem solving if you don't have any. So okay, so let's move to problem solving session. So yeah, so uh, consider a abrupt. So this problem, we need to consider this kind of junction. Consider a abrupt silicon PN junction with doping profile as shown in the figure below. Based on the doping profile, answer the question that follows. So basically, abrupt junction is the junction where the doping profile abruptly, like doping profile is abrupt. So the junction is very weak, but ideal case it's not like that. So basically, like when you do to make the pre-PN junction, basically what you do, you make a region here like this, and then you create this window by some photoresist material, and then you do the diffusion here. So initially starting substrate is your p-type or whatever the complementary substrate you have. So this already has uh, your your like acceptor type dopants are already doping. So now when you start introducing n-type dopant from here, so what will happen like this, nd minus na if you put, so then the like if you plot this profile, so this nd minus na, so basically like at the baseline, so the junction is so basically at the baseline your profile is na at the bulk of the junction, and this side you are introducing a dope. So this does not follow very sharply actually, because this is the because of the physical process diffusion or that, you can't achieve like this kind of profile actually. It's like it's not magic kind of, like you basically how you do the diffusion, you introduce particle from here, and then you leave it for high temperature, they diffuse. But at the junction, this profile will not be that sharp, it will be a bit like staggered kind of. So that is the in real sense the junction will look like this, and the uh, 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 your profile may not be here. But this kind of junction is very hypothetical, and but and best to understand like your concept actually. So basically, like you can get the conceptual understanding very good with this kind of uh, simplified doping profile, so that you don't have lack in uh, basic understand. So, like this kind of doping profile, basically you have uniform doping in the N side, uniform doping in P side. What will happen? Some movement of electron will take place, and your since your ions are dopants are uniformly distributed through the semiconductors, so this charge, whatever the density is, will be flat. So that's what it's the nd minus na. As you can see, it's very sharp at the junction. But ideally it's not like that. It just goes like this. Practically it goes like this. Ideally this is like that. So that is the case. So so the in this case basically in the this right side, x is greater than 0 is doped with the donut type, and x less than 0 is doped by acceptor type. So the as we can see previously, the acceptor side will have a negative charge and donor side will have a positive charge. And with the scale also you can see like this ND, this distance from 0 to ND is less compared to the 0 to NA. So this means like you will have more more doping in the p side and less doping in the n side. An ideal law of junction is basically you should maintain the charge neutrality condition, and that will lead to nd times xn equals to na times xp. So now if your na is higher x, so you can write xp by xn is your ND by NA. So so this is the ratio of this. So if you have NA larger, acceptor type doping larger, then XP will be XP by XN ratio will be smaller, and you can say the bit depletion bit in XN X side will have larger compared to the P side. So the depletion bit in N side in this case will be larger and depletion width in P side will be larger. So which are the option? So this has the same. So this is correct, wrong, and this is also same. This is also wrong, and ideally this also has same. This is also wrong. So the correct answer you will get with this only. Yeah, and the let's just verify because right side ND it will have positive immobile charge carrier. So this the density will be positive in the right direction and negative in the left direction. So the correct answer is B. This junction, this width will be less and this width will be high because Na is greater than Nd. If you are provided with the other case, then you need to choose the option correctly, and you should take focus more attention on this. So I hope this is clear. Yeah. Okay. So uh, let's move to next problem. Identify the corresponding electric field profile in the PN junction in the figure 2. So so the correct field profile how to get. So basically like now we got the charge profile. So basically this is larger and this is q and d, and this is smaller and this is minus q and a because charge in the due to in the p side region will be smaller. And like you can apply the Gauss law. So basically dE by dx is basically q or rho by epsilon, where rho is your surface charge density. So basically then you can convert this and you can take you can integrate this field. So in different region you need to integrate. So so in the uh, charge profile rho is q n d by 10. It's q n d in x greater than 0 less than equals to xn, and is minus q n a on x greater than equals to minus xp less than x 0. So this is minus xp and this is xn. So now we can integrate this equation. So dE by dx is will integrate. So E will become integral of rho dx by epsilon, and rho is basically your q and d. So this is constant. So this integral will become q and d by epsilon x plus c in the positive direction. Similarly, in the e at in the negative direction, it will become minus q and a x by epsilon plus C2, let's say call this is a C1. And also you have one boundary condition at x equals to xn, electric field is 0. So that if you put x equals to xn, then you will reach uh, C is basically minus q n d by epsilon xn, and similarly C2 will be uh, this x equals to minus xp. If you put, then it will become minus q n a xp by epsilon. So your field profile in this will become uh, q n d by epsilon x minus x minus xn, and electric field profile in q n a by minus q n a by epsilon. It will become x plus xp. So this is the profile, and if you can see the field for just yeah. So the field profile. Field profile, if you plot with this equation, then basically at 0, this boundary case, if you calculate at x equals to n, field is 0, at x equal to xn, field is 0, x equal to minus xp, field is 0. And as you see, like this has a positive slope, so this the field profile will have a positive slope like this, and this side this has a negative slope. This is this, and this slope is basically your charge. So ideally I should draw a little bit on the scale. Yeah, so this side actually this side with so this this side width will be bit larger because nd is nd is less than na. So this will have a sharp profile. So this you can choose from the option like this. Both side the field profile is same. This is not correct, and this is a particular example. The field discontinuous exists in case of uh, discontinuous field exists if you have a very strong charge exist at the interface. Similarly, this is also wrong because x side depletion width is smaller compared to the p side, and then this is wrong. And the only correct option is first one. So the correct answer is A answer. So let's move to next problem. The doping profile of a hypothetical silicon PN junction is shown in figure below. Based on the doping profile, answer the question below. So the doping profile here is one side is linearly increasing, other side is flat. So this side is uniform doping case. So if you dope all the acceptor atoms uniformly, then that is the case. And this side it's linearly grading. So it's linearly increasing doping profile. So this side basically so if you plot the charge is like from the charge in the uh, uh, charge in this will be uh, uh, it's like it's in the positive direction, it will be q n d minus n a x by q n d minus n a x, and the other side it will be minus n a times q. So this is the charge profile. And when you integrate this kind of charge profile, so now similarly you can apply the e by dx equals to rho by epsilon. and rho this side if you right side if you integrate. So this mm, so this side uh, it's this side so it's the charge profile is minus Na minus sorry just wait. Yeah, so this side is minus Na, and uh, this side it will increase as the linear grouping, and you can assume this slope constant to somewhere. So now if you so this you can write, or simply you can write q times m times x, where m is the slope of this line actually. So now you can apply this Gauss law in this two direction. So basically for E we will get from x equals to 0 to x equals to xn, and the doping profile is q times m times x divided by epsilon dx, and this will become uh, so this will become so now if you can get this fill this you will get q times m times x squared by 2 epsilon plus c. Now at the edge of the edge of the depletion region E is 0. So at x equals to xn, your E is 0. This implies that C you will get minus q m xn square by 2 epsilon. So now if you put back, then you will E for x greater than x between 0 to xn, you will get q by m divided by 2 epsilon time x minus xn, x square minus xn square. Similarly, other case you will get the profile as q it will be minus so it will be q times na q times na by epsilon, so it is x plus xp, and basically your minus is there, so you can take or so you can take the xp as a sign, and you can take this side because this xp is negative, and for x is greater than so x is between 0 and minus xp. So this whole term will be negative, and this field profile will be negative. So and it will vary very uniformly. So so the so the question in the first question it is asked to plot the charge profile. So because this is uniformly doped, the charge profile you will get from here. It is in p side it's negative, so the negative this option is wrong. And because in this both the profiles are symmetric, this side this is also wrong because right side it's linearly graded doping, and the left side is uh, it's uniform doping, and this is also wrong because in according to this both the sides should have linearly doping. So the correct answer is first one. So the A answer is correct one. So yeah. So if you have any doubt, then you can ask. Otherwise, I will move further if you don't have any doubt. Okay. So let's move to next part. So we from the integration we got the field profile as q n a by epsilon x plus xp, where xp is negative. So at x equals to minus xp, the field will be 0, and so no this if you take minus yeah, so you need to take this negative sign, so because then the slope will be negative, so here also minus sign will come. So when uh, when x equals to minus xp, then your field will be 0. And as you can see, this is the equation of minus q n a by epsilon x minus xp. So this is the equation of y equals to mx plus c kind of equation. This c is minus xp, and then you can compare this slope will be constant, and the slope is this one. So this is a straight line equation, and with the negative slope. So the field is here, and you can draw a line passing through this point and have a negative slope. Similarly, so the electric field in the positive side was q n d by 2 epsilon x square minus x n square. So this you can see like this. This is the equation of parabola y equals to k times x square minus some constant x square minus c. So this parabola has upward curvature and will be shifted in y direction in the negative direction. So this will look like this and will be shifted. So at x equals to 0, if you put, then you will get electric field is minus q times n by twice epsilon minus xn square. So this is the field, and then in the positive direction it will go to this, and at x equals to xn, if you put, then this will become 0. So this field will become like this. So as per this, the this answer is wrong, and this answer is wrong. This is also wrong, because then you need both side linearly created junction. This is also wrong, and this is wrong because the sign of field is wrong, because yeah, then this is wrong, and the correct answer will be first one. So if you have any doubt, you can ask, or if you don't have any doubt, then I will pause for some time, and then we will move next. So let's move to next problem. The doping concentration. This question is for 6 to 9. We need to take the same parameter. The doping concentration of abrupt p-n junction. So this abrupt is given. p-n junction at room temperature. Na is acceptor type. Na is 10 power 12 per centimeter cube, and Nd is 10 power 16 per centimeter cube. So see, like the Na and Nd, the order of difference is 4 order of difference is there. So uh, 4 order difference means like it may be like this junction, or n plus p kind of junction it will be there. So take the intrinsic carrier concentration of undoped silicon as Ni, then Kt by Q is 25 milli-electron volt, epsilon Si, and others. Depletion width of the p-n junction is given. The built-in potential voltage uh, of the p-n junction is given. So to calculate the built-in voltage, you the Bi basically you need uh, so you need Kt by Q ln. So it is p naught by p n naught, or you can write another way also, Kt by Q ln n naught by n p naught. So if you reach from this both the side, you will get the same answer. So basically, if you p naught will be p naught is approximately equals to Na if you assume complete ionization. If you assume complete ionization, Pp naught is Na and Pn naught. So the whole concentration is N side. So that is equals to Ni square by Nd. And similarly, Np naught is N naught is Nd and Np naught is Ni square by Na. So if you put this into this, then you will get the Kt by Q ln. So this Na by Ni square by Na equals to Kt by Q ln Nd by Ni square by Na. So this, if you simplify, then both the cases you will get Kt by Q ln Na Nd by Ni square. So does not matter which carrier you consider. If you assume complete ionization, then the built-in potential will remain the same, and that is the equation. In if you this is Ni square, this is Ni square. Yeah. So if you plug in the values, so if you plug in the values, then this is 25 milli electron volt, or you can write 0.025 ln this the Na is given as 10 power 12 and Nd is given as 10 power 16, and this Ni square Ni is given 10 to the power 10, so this will become 10 to the power 20. So this will become uh, minus Kt ln ln this will become this will become 10 power 8, or this will become 8 Kt ln 10, and this is around 60, and just yeah, so this is 8 times 60, so this is 60 millivolt. So remember this number. So Kt ln 10 is around 60 millivolt. So like this is quick in like solving exams, you remember this number. This is very helpful in like a lot of places. It helps actually a lot. So then you multiply by 8 times 60 millivolt, and this will become 480 millivolt, and this will become 0.48 volt. So the 48, or the closest answer is 46. Like this is roughly this is 60 millivolt, but exact also you will get the same. But for this kind of quick problem solving, you can take help of this, and this is helpful in calculating subthreshold slope and other things. This number is very important, like especially so this Kt ln 10, and this is quite important number. So now uh, yeah, so now let's just move to next problem. So this it is asked to plot the depletion bits in the n side of the junction. So Wn is asked. So basically, total depletion width is basically is Wp. So Doppler depletion width is Wp plus Wn, and from the charge neutrality condition, you can write Na times Wp equals to Nd times Wn. So for to calculate Wn, you can substitute Wp here in terms of Wn. So W will become nd by na wn plus wn, and this will become nd plus na by na times wn, and if you simplify wn will be na by nd plus na times w. So W is we are given NA as 10 power 10 and ND is 10 power 16. So NA is 10 power 12, ND is 10 to the power 16, and you can see like you to calculate you can neglect like from denominator you can neglect Na with respect to ND. So you can write this approximately equals to Na by ND times W. So this Na by Nd is 10 power 12 and divided by 10 power 16 times 24 and micrometer, and this will become 10 power minus 4 times 24 point something. So this depletion rate is given 24.6 micrometer, and this will become 2.46 into 10 power minus 3 micrometer. So this the correct answer is this one. Similarly, in the p side, you can replace you can substitute xn as nd by na times no na by nd times xp. So then w will become this wn. So then w it will become wp times nd by na by nd plus 1, and wp will become nd by na plus nd times w. So now you can neglect na compared to nd because 4 order of magnitude difference is there. So then it will become roughly equals to nd by nd times w, and this will get cancelled. It will be equals to w times wp will be similar to w. So this will be equals to 24.6 micrometer. So the correct answer will be this. And you can see because this p type is lightly doped case, so this is n plus p kind of junction in which the depletion width is in the p side is larger compared to the depletion width in n side, which is has very sharp density, and this is like this. So this is the case of heavily and lightly doped junction or single-sided junction. You say this case of single-sided junction. Yeah. So this is the case, and then you can calculate the magnitude of electric field across the junction. So you can calculate the E from our equation we have derived. So at the junction, so the electric field was qnd by epsilon x minus xn. So at x equals to 0, it will become minus qnd by epsilon xn, and xn you have seen from that figure. And if you plug in the value of epsilon silicon, this is epsilon silicon, q is the electronic charge 1.6 into 10 power minus 19, and the nd is 10 power 16. Xn we have calculated 2.46 into 10 power minus 3, 46 into 10 power minus 3. And then this the basically here you need to do unit conversion because the uh, because this is given epsilon is given in farad per centimeter. Then you need to take the width unit also in centimeter, so that you will get the final field profile as volt per centimeter. So be aware of the unit. Actually this problem is mostly about the unit. And if you plug in value correctly, then you will get the answer correct. That is the correct answer. So this, if you have any doubt, I will pause for some time and then we will move to next problem. So yeah, so let's move to next problem. So consider a P1 P2 side type of junction isotype. So basically isotype junction, here both the region have actually similar kind of doping profile, but there is a difference in the doping concentration actually. So this is also, this side is also dope, acceptor type, this also dope, acceptor type, but Na1 is greater than Na2. So this will have more p-type behavior. This is a less p-type behavior. So now, as you increase the doping, then your Fermi level will move closer to the valence band. So let's draw the without junction band diagram. So the correct procedure, like initially when you start band diagram, you draw without contact band diagram. Suppose you did not make the band diagram, make the contact, then you can then you make the contact band diagram, so that you will get a clear understanding. So now because both side the silicon is the same, uh, yeah, both side, sorry for disruption. Yeah, so both side, since the material is silicon, so this will have the same uh, same uh, same conduction band, same electron affinity chi, and then you can draw the valence band similarly because valence band is fixed. Then in case of this right side, the one is the heavily p type dope, so this will have the Fermi level closer to the valence band ef1, and this is the Fermi level will be a bit away, so this is ef2. So now if you join this junction because the gap is there, then this if you make the joint band diagram, then you will draw the Fermi level as fixed, the Fermi level is constant EF, and this is the junction. Then the this side the band will go band down, and this side band will be, so it will be like this, and here it will be like this, and then you can join by like this, so it will be like this. So this will be no, just no, this is wrong. No. Yeah. So this will be so this this side band will bend down, and this side band will move up, and this side um, here uh, the in the away from the junction, uh, the uh, the Fermi level will lie closer to the valence band, and at the near the junction Fermi level will lie a bit away from the valence band, and then at the depletion you can join this band, and this you will get like this profile. Similarly here you can write like this profile, and the vacuum level also, if you want to draw, then you can draw this. So this vacuum level banding is BBI, and this is chi, and which is always remain fixed. So this if you draw by this, then you won't be having any problem. If you, even if both the sides is not given as the same silicon material, If even if different material also is given, or heterostructure band diagram, that you will draw it correctly if you follow this procedure actually. Otherwise, you will make a mistake, and that will lead to penalty points in your exams. So that you can write here. The correct picture will be this one. Like this is wrong. This is wrong. This is also wrong. This is wrong because EI is not banned, and this side is opposite band, but that can be true. This side is same kind of banding is there, so that means the correct answer is this one. So yeah, so uh, okay, so uh, let's move to next problem, and this was 2018 gate problem. A junction is made by P minus silicon with doping density this, and with the P type silicon with doping density this. Assume Kt is this, then this is 300 Kelvin, the magnitude of built-in voltage. So so this is P1, it is equals to 10 power 15 per centimeter cube. P2 is 10 power 16 per centimeter cube. And if you want to calculate the built-in potential between 2 and 1, then you can calculate VBIV equals to KT by Q, ln, KT by Q ln P2 by P1. And this, if you calculate KT by Q ln 10 to the power 16 divided by, no, this is 17, 10 to the power 17 divided by 10 to the power 15, this will become 10 to the power 2, and 2 you can take out the log, so this will become 2 times KT by Q ln 10. And as we have seen, like this number is very important, this is around 60 millivolt. So this you can write as 120 millivolt or 0.12 volt. So the correct answer will be this. That's how you can solve it very quickly. Yeah. So that was the problem for this set. Actually, this was some of the sample problem corresponding to this weak problem set. And we can so if you have any doubt, you can ask. I will pause for some time. Any doubt related to previous session or this session, or yeah, whatever, or in lecture series, if you have any doubt, you can ask. I will pause for some time. Okay, so if you don't have any doubt, then we can end the session. We will meet the same time at the same platform. Till then, have a nice week, and try submitting your assignment or type. And you can ask the question in the next session related to this week assignment deadline. And for that time, like, keep enjoying learning. Thank you so much for patiently listening, and we will meet the same platform at the same time. Thank you so much. Bye. Have a nice. Uh, Someone joined just now. Computer. Yeah. So, if anyone has doubt, I can clear. I will wait for some time. I see some people are joining now also. Yeah, that is fine. Okay, thank you so much for. If you don't have any query, and if you have any query, then post to the forum. We will reply. And till then, thank you so much, and have a nice learning and nice week. Thank you so much. Bye. We can end this session.